Rahim. In this part we are going to talk about different atomization methods in atomic spectroscopy. As I said before, in atomic spectroscopy we have to vaporize the sample and atomize it, and then measure the absorbance or emission or fluorescence. There are many different atomization methods which are used in atomic spectroscopy. In this table, you can see the most important ones. For example, flame is the most common method for atomization. Then we have electrothermal vaporization. We have plasma methods like inductively coupled plasma, direct current plasma, micro-induced plasma, and then we have glow discharge, electric arc, and electric spark. Now we are going to talk about flame atomization. In flame atomization, we use a flame to heat the sample and atomize it. Here you can see picture of a flame burner that is used in atomic spectroscopy. A flame atomizer will usually have a long, narrow burner head that serves as a sample path. Usually it's a 10 centimeter long burner head. Sample is introduced via aspiration. So we have a nebulizer in the entrance of the sample. The nebulizer controls sample flow, producing a mist. The mixing chamber assures that the sample mixes with the oxidant and fuel prior to entry into the flame. So in the mixing chamber we mix the sample droplets, fuel, and oxidant, and this mixture will introduce into the burner head, and we will have the flame over there. Here also you can see another picture of the flame atomization, and you see the flame that is a narrow and long flame, usually with 10 centimeter length. Flame atomic absorption spectroscopy, or flame AAS, has several advantages. It is a robust method. Its use is easy with fast analysis time. It's a fast method and modest cost. It is not so expensive, but it has some disadvantages. For example, its detection limit is not very low. It is usually in the ppm level, and we use the flammable gases that can potentially be dangerous. The number of atoms of an element excited by the flame depends on flame temperature and the energy difference between the excited and ground state. Or we can say it depends on the element type, because some elements need less energy to be excited or to be atomized, but some of them need more energies. For example, alkaline elements can be excited very easily with a lower temperature, but some elements require more energies. Here you can see different parts of an atomic absorption equipment. In the left side you can see the source lamp, and then we have the chopper that is used for modulation of the light of the lamp. Then we have the sample that here in this picture it's a flame. Then we have the monochromator, and then we have the detector. About the chopper, I can explain something for you. Chopper is, as I said, is used to modulate the light of the lamp, of the source lamp. But why should we modulate the light of the lamp? You see, we have the emission of the lamp, and then we have the emission of the flame. In atomic absorption spectroscopy, we should distinguish between these two emissions, and chopper is the device that do this for us. You see, a chopper will make the light of the lamp to an AC light, alternating current light, but the light of the flame is continuous, it is DC. So then the detector can distinguish between these two lights. In another word, we can say that the chopper is used to remove the background emission of the flame. The chopper is used to remove the background emission of the flame. In this way, we will have only, we can measure only the emission of the source lamp and distinguish it or discriminate it from the light or emission of the flame. Now we are going to talk about flame structure. A flame has three important regions. The first region is primary combustion zone in the bottom of the flame. That is the temperature in this region is not very high. Thermal equilibrium is ordinarily not reached in this region, and it is therefore seldom used for flame spectroscopy. Then we have in this picture, you can see the primary combustion zone in the lower part of the picture. Then we have internal region, interzonal region. That is the most important region for a measurement of the absorbance, because in this region the temperature is higher and the sample has been atomized. Then we have the secondary combustion zone in the higher levels. That is not appropriate region for absorbance measurement, because in this region there is a possibility of oxidization of the sample, because the flame is in contact with the atmosphere, with the air, and the sample atoms can be oxidized by air. So the most important part of the flame for measuring the absorbance is the interzonal region. Sorry. As you can see here, in the interzonal region, this area is relatively narrow in stoichiometric hydrocarbon flames, and is often rich in free atoms, and is the most widely used part of the flame for spectroscopy. And then we have secondary combustion zone. As I said, in a secondary reaction zone, the products of the inner core are converted to stable molecular oxides that are then dispersed into the surroundings. But we have different types of flames, flame atomization emission source. That in this picture you can see the different types of flames according to the type of fuel and oxidant. If the fuel is acetylene gas and the oxidant is air, then we will have a temperature with then we will have a flame with the temperature of 2400 to 2700 degrees Kelvin. If the fuel is acetylene and oxidant is nitrous oxide N2O, then we will have a flame with a temperature of 2900 to 3100. As you can see, the second flame has higher temperature than the first one. These two flame types, I mean the acetylene air and acetylene nitrous oxide, are the most commonly used flames in atomic spectroscopy. But we have other flames also that maybe in some cases are used. For example, acetylene oxygen, hydrogen air, hydrogen oxygen, and cyanogen oxygen. The last one is the most high temperature flame. As you can see, the temperature of a cyanogen oxygen flame is 4800 Kelvin. That is very high temperature, but this flame is not usually used because of its danger. In this picture, you can see the flame profile in atomic absorption and the effect. Actually, here you can see the effect of temperature, effect of height of the burner or height of the flame on the absorbance or on the sensitivity of measurement of an element. For some elements like chromium, using more height is not appropriate. So it's better to use lower parts of the flame to measure the absorbance. If you increase the height of the flame, the sensitivity or the absorbance of chromium will decrease. Uh, for silver, the situation is opposite. So if you increase the height of the flame, the absorbance for silver will be increased. So it is better to use more height of the flame, or to measure silver in the upper levels of the flame. The reason is that chromium can be oxidized easily, but silver cannot be oxidized easily. And for this reason, it is better to use more height for silver and less height for chromium. But for elements like magnesium and many other elements, there is a middle height, medium height that gives you the best absorbance results. Here you can see the temperature profile of a flame. As you can see, in the lower height of the flame, the temperature is low. It is, for example, 1700s, and then it will increase by in the upper levels to 1800s, and then 1830 and 1863. That is the highest temperature for this flame, and then it will decrease again in higher levels, because when you go to the higher levels of the flame, again you will have lower temperatures. Here you can see the picture of 4 different flames. In the left side, we have a cool flame with less air and more fuel. When you increase the concentration of air or the oxidant, the flame will be more hot. So in the right side, you can see a hot flame which is rich in oxidant. Here also you can see an oxygen-rich mixture that has more oxygen and less fuel. That is a hotter flame. But here you can see a fuel-rich mixture with more fuel and less oxygen. This is a flame with a lower temperature. Here you can see the structure of a nebulizer. It's a concentric nebulizer that we already explained for you the structure of it. This nebulizer is used for injection of the sample into the flame, and as we have explained before, the nebulizer can convert the sample to tiny droplets or to a mist. Here you can see the atomization steps or procedure. At the beginning, we have a solution that by nebulization it will be sprayed into the burner. After entrance of the sample droplets to the flame, we have the dissolution of the sample, that the sample will be converted to a solid or gas aerosol. Then we have volatilization step, that the sample will be converted to gaseous molecules. And then we have the dissociation step, that the gaseous molecules will be converted into atoms. And if we increase the temperature even more, the atoms also can be converted to atomic ions. And each of these gaseous molecules, atoms, and atomic ions can be excited by in higher temperatures and emit the light. So they can both emit or absorb the light. We have two types of flame atomizers, or two types of burners. The first type, that is a very simple type, is called total consumption burner. In this type of burner, the fuel and oxidant gases and the sample will be mixed directly in the flame, and not before reaching to the flame. So this burner is not a good burner, because all the droplets of the sample, I mean the small and big droplets, all of the droplets will be directly enter to the flame, and some of the droplets will not be atomized because they are big droplets, and this will decrease the sensitivity. This will reduce the temperature of the flame, and it's not so appropriate. This type of burner is a very noisy burner also, and it's not usually used anymore for atomic spectroscopy. But the burner that today is used is this one, that is called premix or laminar flow burner. As you can see in this burner, we have a mixing chamber that first we have the nebulizer, and then the oxidant and fuel will be mixed with the sample droplets and in the mixing chamber, and then we have some mixing baffles that can remove big droplets, and only very, very small and tiny droplets will reach to the flame. So we will have a laminar flow, and we have a laminar flame. We have a good flame with reproducible results, and higher sensitivity with this type of burner. The advantage of this type of burner, I mean the laminar flow burner, is a uniform drop size, homogeneous flame, quiet flame, and a long pass length. But its disadvantage is the possibility of flashback of the flame and explosion if the rate of burning is higher than the rate of gas flow. I mean, if the gas flow is not enough, then the flame can flash back into the mixing chamber, and we may have explosion. So it is more dangerous. One of the disadvantages of this burner is that it is more dangerous than the total consumption burner. Another disadvantage is that about 90% of the sample is lost because, as I said, the big droplets will be removed and only very tiny droplets will reach to the flame. So about 90% of the sample will be lost, and we have a large mixing volume also in this method that will take time to replace one sample with the next one. In atomic absorption spectroscopy, we can the atomic absorption spectroscopy method is mostly used for quantitative applications. Quantitation with atomic absorption and with flame atomic absorption has an LOD or limit of detection between 1 to 20 90 gram per milliliter or 0.001 to 0.020 ppm. So the LOD or detection limit of the sample is in this region, and its relative error is 1 to 2%. That is a very, very good result for this method. It means that the reproducibility, the repeatability of the method is good. A standard deviation of it is very low. This is the lamp that is used in this method. We have already explained this type of lamp that is called a hollow cathode lamp. Sometimes this type of lamp also is used, that is EDL lamp. We have already explained this type of lamp for you. Here you can see some of the applications of flame atomic absorption spectroscopy. These applications include clinical analysis, environmental analysis, analysis of pharmaceutical samples, and industry or automobile industries that are when we want to measure elements, we can use flame atomic absorption spectroscopy for it. Okay, that was the last slide about flame atomic spectroscopy, and now we are going to speak a little about another method that is called hydride generation technique. What is hydride generation technique? You see, in the flame atomic absorption spectroscopy, the sample solution will be introduced in the nebulizer and into the flame, and we directly enter the sample solution to the flame. But in the hydride generation technique, we make this, we convert the sample to a hydride, and this hydride can be converted to a gas. So we will not enter the solution into the flame or into the atomizer. Instead, we can just enter the gaseous hydride of the sample. So this method is much better with much higher sensitivity, but it cannot be used for all the elements. It is used just for a few of the elements that their hydrides are volatile and can be volatile easily. So as you can see here, hydride generation technique provides a method for introducing samples containing arsenic. These are the elements: arsenic, antimony, tin, selenium, bismuth, and lead, and a few other elements into an atomizer as a gas. Volatile hydrides can be generated by addition of an acidified aqueous solution of a sample to a small volume of a 1% aqueous solution of sodium borohydride. Sodium borohydride can reduce the sample, reduce the element to a hydride in an acidic media. And as you see in this equation, BH4 minus plus 3H plus plus 4H3ASO3 can give 3H3BO3 and 4ASH3. This ASH3 is the hydride of arsenic. That is volatile and can be evaporated easily, and can be this gas, and we convert it to a gas, and this gas can be conducted to the flame or to an atomizer, and then we can atomize it and measure its concentration. The volatile hydride, in this case arsine, is swept into the atomization chamber by an inert gas. Here you can see a very simple type of hydride generation technique. You see we have an acidic solution in an Erlenmeyer, and from the top by a syringe here we can inject a mixture of the sample and NaBH4. This should be NaBH4, not Br4. This is something wrong. It should be corrected. So we have a mixture of sample and sodium borohydride that can inject it into the solution, and then we have a inert gas. By the help of the gas, the hydride of the sample will be conducted to a quartz absorption tube that is heated on a flame. So the quartz tube is heated by the flame, and the hydride of the sample will be entered to this tube and will be atomized, and then we will measure the absorbance. So as I said, this method is much more sensitive than the flame atomic absorption spectroscopy, and it is free of interferences. So in flame we may have some interferences from the solution, but here we don't enter the solution to the flame. Therefore, we may have less interferences from the matrix. In this picture, you can see another type of hydride generation technique that is called continuous method. In this method, also we have sodium borohydride and acidic solution and sample, but the mixing of the solutions with sodium borohydride are by the help of some peristaltic pumps. So we have here 3 pumps. That one pump is pumping HCl solution, one pump is pumping the sodium borohydride solution, and one pump is pumping the sample solution, and then they will be mixed together and entered again this absorption tube that is heated on a flame. So this is just for make the things more easy and automation of the technique. In the hydride generation technique, one of the problems is that the oxidation state of the elements can influence the sensitivity for some of the elements. So we should be careful when we use this method. The efficiency of hydride formation depends on the oxidation state of the analyte. In the case of germanium, tin, and lead, the oxidation state has no influence on hydride formation. So for these three elements, germanium, tin, and lead, we have no problem. But about arsenic, the sensitivity of arsenic 4 is about 50 to 80% of the sensitivity of arsenic 3. The sensitivity of antimovan Sp5 is about 50% of the sensitivity of antimovan 3. And for bismuth, bismuth exists only in the trivalent oxidation state. So for bismuth also we don't have any problem. For selenium and tellurium, the difference between the oxidation states 4 and 6 is very pronounced. So we always should convert selenium and tellurium to oxidation state of 4, because this oxidation state has very higher sensitivity. So when we use different elements, we should be careful about their oxidation states in the hydride generation technique. We have another method that is similar to hydride generation, but is used only for mercury. This technique is called cold vapor mercury. You see, if we decrease ionic mercury to its element or to its liquid element, or Hg0, then mercury, as you know, is the only element that is liquid. Mercury is the only liquid element. All of the other elements are solid, but mercury is liquid. And it has a relatively high vapor pressure. So if you convert ionic mercury to the elemental mercury, it can be evaporated from the solution, and very easily you can measure its absorbance without needing to any flame. It is because and for this reason it is called cold vapor mercury, because its vapor it doesn't need any temperature. You don't need any flame or other temperatures. You just can measure the absorbance of the vapor by reducing the ionic mercury to elemental mercury. But for this conversion, you can either use tin SN2+, or you can also use sodium borohydride. So if you add sodium borohydride or tin 2+ to the mercury solution, it will be converted to liquid mercury, HGl. And this liquid mercury can be evaporated and be conducted to the atomization tube, and without heating of the tube you can measure its absorbance. And this is a method that is used only for mercury. This was the last slide. Wassalamu alaikum.